To calculate alternate parallel feeders, firstly, calculate the total cross-sectional area of the original feeder. Each number 350 cm conductor has a cross-sectional area of 225.2 square millimeters. The total area of three number 350 cm conductors is 225.2 square millimeters times 3, which equals 675.6 square millimeters. Secondly, choose suitable smaller conductors. Consider conductors with cross-sectional areas approximately half of number 350 cm. Suitable options include 2/0 AWG, which is 167.8 square millimeters, or 250 kcmil, which is 153.3 square millimeters. Thirdly, determine the number of parallel conductors. To achieve a similar cross-sectional area to the original feeder, you will need two parallel conductors for each phase. Therefore, you will need 2 times 2/0 AWG, or 2 times 250 kcmil for each phase. Fourthly, calculate the conductor ampacity. For 2/0 AWG, the ampacity in THHN into and 1/2 inch conduit is 135 amps. For 250 kcmil, the ampacity in THHN into and 1/2 inch conduit is 150 amps. Fifthly, determine the phase current. The phase current for a 300 amps feeder is 300 amps divided by 3, which equals 100 amps. Sixthly, size the neutral conductor. For a 3-phase feeder, the neutral conductor size is typically one size smaller than the phase conductors. Therefore, you can use 1/0 AWG, which is 133.1 square millimeters, as the neutral conductor. The final configuration for each parallel feeder should consist of 2 parallel conductors of either 2/0 AWG or 250 kcmil THHN, 1/0 AWG neutral conductor, and 1 number 4 ground conductor. 2 separate 2 and 1/2 inch conduits would be required for the 2 parallel feeders. It is important to note that the above calculations and recommendations are approximate. Always consult applicable electrical codes and standards for specific requirements and safety considerations. Parallel feeders should be properly bonded and grounded according to code regulations. To elaborate further on conductor sizing, it's essential to understand the concept of ampacity, which is the current carrying capacity of a conductor in amps. Ampacity is influenced by several factors, including the conductor's material, size, insulation type, and the surrounding environment. The National Electrical Code, or NEC, provides tables that list the ampacities of various conductors under specific conditions. For example, NEC Table 310.16 lists the allowable ampacities of insulated conductors rated up to 600 volts, not more than 3 conductors in a raceway or cable or earth, based on ambient temperature and conductor temperature rating. When sizing conductors for parallel feeders, it's crucial to ensure that each parallel conductor is capable of carrying its share of the total load current. This involves dividing the total load current by the number of parallel conductors to determine the minimum ampacity required for each conductor. In the given scenario, the original feeder is rated for 300 amps. If 2 parallel feeders are used, each feeder must be capable of carrying at least 150 amps. The choice between 2/0 AWG and 250 kcmil conductors depends on factors such as cost, availability, and the specific requirements of the installation. Both conductor sizes have ampacities greater than 150 amps when using THHN insulation in 2 and 1/2 inch conduit, as mentioned earlier. THHN insulation is a popular choice for electrical wiring due to its high temperature rating, moisture resistance, and overall durability. It is commonly used in both dry and wet locations, making it suitable for a wide range of applications. When installing parallel feeders, it's essential to ensure that all conductors are of the same material, size, and insulation type. This helps to ensure that the current is evenly distributed among the parallel conductors, preventing overloading and potential hazards. Additionally, all parallel conductors should be terminated in the same manner to ensure equal current sharing. Proper bonding and grounding are also critical for parallel feeder installations. Bonding refers to the process of connecting all metallic parts of the electrical system together to create a low impedance path for fault current. Grounding refers to the connection of the electrical system to the earth, providing a path for fault current to flow back to the source in the event of a ground fault. The NEC provides specific requirements for bonding and grounding parallel feeder systems, including the size and type of grounding conductors required. These requirements are designed to protect people and equipment from electrical shock and fire hazards. In addition to conductor sizing, ampacity, and bonding and grounding, conduit fill is another important consideration when designing parallel feeder systems. Conduit fill refers to the percentage of the conduit's cross-sectional area that is occupied by conductors. The NEC limits the maximum allowable conduit fill to prevent overheating and damage to conductors. The NEC specifies the maximum allowable conduit fill based on the type of conduit and the number of conductors it contains. For example, for 3 or more conductors in a conduit, the maximum allowable fill is typically 40%. When calculating conduit fill, it's important to use the correct dimensions for the conductors and conduit being used. These dimensions can be found in the NEC or in manufacturers' catalogs. In the given scenario, the original feeder consists of 3 number 350 MCM conductors and 1 number 4 ground conductor in the 2 1/2 inch EMT conduit. EMT, or electrical metallic tubing, is a type of rigid metal conduit that is commonly used in electrical installations. If 2 parallel feeders are used instead, each feeder would consist of 2 2/0 AWG or 250 kc mil conductors, 1 1/0 AWG neutral conductor, and 1 number 4 ground conductor. These conductors would need to be installed in separate 2 1/2 inch EMT conduits to comply with conduit fill requirements. It's also important to consider the voltage drop in parallel feeder systems. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for feeders and 5% for branch circuits. To minimize voltage drop in parallel feeder systems, it's important to use conductors of adequate size and to keep the length of the feeders as short as possible. Voltage drop can be calculated using various formulas and online calculators. In addition to the technical considerations mentioned above, it's also important to consider the cost and practicality of using parallel feeders. While parallel feeders can be a useful solution in situations where space is limited, they can also be more expensive and complex to install than a single, larger feeder. Before deciding to use parallel feeders, it's important to carefully evaluate all of the available options and to choose the solution that is most cost-effective and practical for the specific application. Finally, it's important to remember that electrical codes and standards are constantly evolving. It's essential to stay up to date on the latest requirements and to consult with a qualified electrical professional when designing and installing electrical systems. The NEC is updated every 3 years, and it's important to use the latest edition to ensure compliance with current regulations. Local codes and regulations may also vary, so it's important to check with the local electrical inspector to ensure compliance with all applicable requirements. In summary, calculating alternate parallel feeders involves several steps, including determining the total cross-sectional area of the original feeder, choosing suitable smaller conductors, calculating the conductor ampacity, sizing the neutral conductor, and ensuring proper bonding and grounding. Conduit fill and voltage drop are also important considerations. It's essential to consult applicable electrical codes and standards and to work with a qualified electrical professional to ensure a safe and compliant installation. By following these guidelines, it's possible to design and install parallel feeder systems that meet the needs of the application while ensuring the safety of people and equipment. Always prioritize safety and adhere to all applicable regulations when working with electrical systems. Now let's elaborate a bit more on each step. Firstly, determining the total cross-sectional area of the original feeder is crucial for ensuring that the parallel feeders have the same current carrying capacity as the original feeder. The cross-sectional area of a conductor is directly related to its ampacity. A larger cross-sectional area means a lower resistance and therefore a higher ampacity. Using the cross-sectional area of the original feeder as a starting point ensures that the parallel feeders are adequately sized to handle the load. Secondly, when choosing suitable smaller conductors, it's important to consider the availability and cost of different conductor sizes. While 2/0 AWG and 250 kc mil are both suitable options in this scenario, one may be more readily available or less expensive than the other. It's also important to consider the ease of installation. Smaller conductors may be easier to work with, especially in tight spaces. Thirdly, calculating the conductor ampacity is essential for ensuring that the conductors are not overloaded. Overloaded conductors can overheat, leading to insulation damage, fire hazards, and equipment failure. The NEC provides ampacity tables that list the allowable ampacities of conductors based on their size, insulation type, and installation conditions. It's important to consult these tables to ensure that the conductors are adequately sized for the load. Fourthly, sizing the neutral conductor is important for ensuring proper system operation. The neutral conductor carries the unbalanced current in a three-phase system. In some cases, the neutral conductor may need to be the same size as the phase conductors. However, in many cases, the neutral conductor can be smaller than the phase conductors. The NEC provides specific rules for sizing the neutral conductor based on the type of load and the characteristics of the system. Fifthly, ensuring proper bonding and grounding is critical for safety. Bonding and grounding provide a low impedance path for fault current to flow back to the source, tripping the circuit breaker or fuse and de-energizing the circuit. This protects people and equipment from electrical shock and fire hazards. The NEC provides detailed requirements for bonding and grounding electrical systems. It's important to follow these requirements carefully to ensure safe and compliant installation. Now let's discuss the importance of consulting applicable electrical codes and standards. Electrical codes and standards are developed by organizations such as the NEC, the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. These codes and standards are based on years of experience and research and are designed to protect people and property from electrical hazards. The electrical codes and standards are constantly evolving to keep pace with new technologies and changing conditions. It's important to stay up to date on the latest requirements and to consult with a qualified electrical professional when designing and installing electrical systems. Local codes and regulations may also vary, so it's important to check with the local electrical inspector to ensure compliance with all applicable requirements. Finally, let's emphasize the importance of working with a qualified electrical professional. Electrical work can be dangerous, and it's important to have the knowledge and experience to do the job safely and correctly. A qualified electrical professional will have the training and experience to design and install electrical systems that meet all applicable codes and standards. They will also be able to troubleshoot electrical problems and make repairs safely and efficiently. Hiring a qualified electrical professional is an investment in safety and peace of mind. In addition to the points already discussed, let's delve deeper into the practical aspects of running parallel feeders, particularly concerning installation and maintenance. When running parallel feeders, meticulous planning is crucial. Before starting any work, a comprehensive site assessment is necessary to identify potential obstacles such as existing utilities, structural elements, and environmental factors. This assessment will help determine the most efficient and safest route for the conduits. The installation process itself requires careful attention to detail. Conduits must be properly supported and secured to prevent sagging or damage. The spacing between conduits should be sufficient to allow for adequate ventilation and to prevent overheating. Bending conduits can be challenging, especially with larger sizes. Specialized tools and techniques are often required to ensure that bends are smooth and uniform, without kinking or damaging the conduit. Pulling conductors through conduits can also be difficult, especially over long distances or around multiple bends. Lubricants can be used to reduce friction and make the pulling process easier. It's important to use lubricants that are specifically designed for electrical conductors and that are compatible with the insulation material. Terminating conductors in parallel feeder systems requires careful attention to ensure proper connections. All connections must be clean, tight, and properly insulated. Torque wrenches should be used to tighten connections to the manufacturer's specifications. The use of anti-oxidation compounds can help prevent corrosion and ensure long-term reliability. Labeling is essential for identifying and tracing conductors in parallel feeder systems. Each conductor should be clearly labeled with its size, function, and destination. Labels should be durable and resistant to fading or damage. Once the installation is complete, thorough testing and commissioning are necessary to verify that the system is operating correctly. This includes testing the insulation resistance of conductors, measuring voltage drop, and verifying the operation of circuit breakers and other protective devices. Regular maintenance is essential for ensuring the long-term reliability of parallel feeder systems. This includes inspecting conduits and conductors for damage, tightening connections, and testing protective devices. Thermographic scanning can be used to identify hotspots that may indicate loose connections or overloaded conductors. Any problems that are identified during maintenance should be promptly addressed to prevent further damage or potential hazards. Furthermore, let's consider the economic aspects of parallel feeders versus a single larger feeder. While the initial cost of materials might be higher for parallel feeders due to the increased quantity of conduit and conductors, there can be offsetting factors. For instance, smaller conductors are generally easier to handle and install, which can reduce labor costs. In situations where space is extremely limited, the cost of modifying the building structure to accommodate a larger conduit might outweigh the cost of running parallel feeders. Another economic consideration is the potential for future expansion. If the electrical load is expected to increase in the future, parallel feeders can provide a more flexible and cost-effective solution than installing a single, oversized feeder. Additional parallel feeders can be added as needed to accommodate the increased load. Moreover, let's discuss the implications of using different types of conductors in parallel feeder systems. While THHN is a common and versatile choice, other insulation types, such as XHHW or RHW, might be more suitable for certain applications. XHHW insulation is known for its excellent moisture resistance, making it a good choice for wet locations. RHW insulation is also moisture resistant and can be used in direct burial applications. The choice of insulation type should be based on the specific environmental conditions and the requirements of the application. It's crucial to ensure that all conductors in the parallel feeder system have the same insulation type to maintain consistent electrical characteristics. Furthermore, let's address the potential challenges associated with voltage imbalance in parallel feeder systems. Voltage imbalance can occur when the impedance of the parallel conductors is not equal. This can lead to unequal current sharing, overloading of some conductors, and reduced system efficiency. To minimize voltage imbalance, it's essential to ensure that all parallel conductors are of the same material, size, length, and insulation type. The conductors should also be installed in close proximity to each other to minimize differences in inductance. In addition to these measures, it's also important to monitor the voltage and current in each parallel feeder to detect any signs of imbalance. If voltage imbalance is detected, the cause should be investigated and corrected promptly. In conclusion, parallel feeder systems offer a flexible and adaptable solution for distributing electrical power in a variety of applications. However, careful planning, meticulous installation, and regular maintenance are essential for ensuring their safe and reliable operation. By adhering to the guidelines outlined in this discussion and consulting with qualified electrical professionals, it's possible to design and implement parallel feeder systems that meet the specific needs of the application while maintaining the highest standards of safety and performance. Always prioritize safety and consult with qualified professionals when working with electrical systems. The concepts discussed here are for informational purposes and should not be considered a substitute for professional electrical advice.